Hi guys, it's Mr. Coon. I wanted to do one more type, there's actually two more, but this one particular type of motion, is going to be a two-dimensional motion. So not only will it be motion going in the vertical, so in the vertical direction, it'll also be motion going in the horizontal direction. So this is a little diagram that I've made of the tallest building, the tallest man-made building as of 2014. It's called the Burj Khalifa. It's in Dubai and it's a ridiculous 828 meters tall, which is a really, really tall building. It's ridiculously tall. And I also, this little part here, I'm just going to omit for now. I'm going to talk about that a little bit later. I just wanted to ask a question. If I were to have someone here, there's like a, let's say it's a helicopter, and another person here on top of the Burj Khalifa. If this person were to kick a soccer ball at a certain speed, in line with the horizontal, horizontal, in line with the horizon, in line with the ground, in that direction, and it's going to do this sort of motion here, it's going to do this elliptical motion, it's going to eventually fall to the ground, and then the person in the helicopter at the same height that it was kicked drops the same type of soccer ball. Which one do you think would actually reach the ground first? That is an interesting, very interesting question, and I might even we might even do something in class to see if we can try to figure that out. But for now, I'll just tell you the answer for now, because intuitively sometimes you may think the one that's kicked or the one that's just free falling. Obviously in this question, one of the assumptions is that air resistance is negligible. So with air resistance, the speed is going to be very much affected. So we, in these simple problems, to simplify, we've got to neglect air resistance. The answer actually is that they will both fall at the exact same time. So this is quite interesting, and we're going to find out a couple of things that are quite interesting about this. So this person here, some of you guys who are actually really into your soccer, did some research on the fastest soccer kicks. This man here from I think Sporting Lisbon is the team. His name is Ronnie Hebison, sorry. He did a penalty goal and clocked at 131 miles per hour, that is also ridiculously fast. So if you convert it, it was 209.6 kilometers per hour. But the bit of data that we need to use is that it was at 58.2 meters per second. So if we put this into a problem, if Ronnie Hebison were to kick that ball off the top of Burj Khalifa in the horizontal direction at his enormous 58.2 meters per second, let's get a couple of things. How far? What would be the distance? Okay, what would be the distance that he would actually kick it in? How far would he kick it away? Also, how long would it actually take for the ball to get to the ground? So if you've been looking at my other videos, especially the previous video, you should be starting to already think of a solution. And if you are, that's awesome. If you aren't, there's no worry. There's no problem with that, because we're going to go through it. So first things first, let's have a look at our assumptions and also our coordinate system. So our coordinate system, we already know that positive is in the up direction, but also because it's a two-dimensional problem, that here we're going to say in the direction that Ronnie actually kicks. So in this particular one, from the left to right, so to the right also is a positive direction. Whenever you're doing a two-dimensional motion, it might seem a little bit complex, and you're going to use a little bit more of a complex mathematics. We need to break it down into two separate motions that have distinctive properties to each other. Okay, so you need to split, anytime you're doing two-dimensional motions, you need to split it up into two different systems. So let's split it up into two different systems. Those two different systems is going to be motion in the x direction. Let's just say that, let me put it in blue, that up and down is the y direction, and going to the right is the x direction, just to make it simple. Okay, just to make it simple. Let's first deal with the downwards direction. Actually, it should be the downwards direction because it's falling. So sorry about the little arrow. It's in the downwards direction. Let's first deal with that. So let's call the velocity. So the downward velocity is going to be its velocity. So let's have a look. The downward velocity is going to be its velocity in the y direction. Okay. And we're also going to have an initial velocity in the y direction. We're going to have a time. Now, time in this particular instance, the time is the one, because it's a scalar quantity, it is the only one that's not going to have a direction. Time will be fairly constant for both motions. So if you look, the distance it covers to the maximum towards the x direction will be the same amount of time that it actually goes to the ground in the y direction. So we can intuitively later we'll find out how far it actually went down to the right. So first off, we've got in the y direction, we know that our acceleration, because it's acceleration due to gravity, in the y direction is going to be negative 1.8 meters per second. And now we know that if Ronnie kicked it in the horizontal direction, okay, if Ronnie kicked it in the horizontal direction at 58.2 meters per second, so we know already, and I'll put it in red, that the initial velocity in the x direction is 58 sorry, there was another 2 there, 0.2 meters per second already, and I'll put a 0.2 here, I apologize. So at the top, what is its initial velocity going to be? We already know that from a free fall, that the initial velocity in the y direction, especially if it's a free fall, is going to be 0 meters per second. So that's going to be easy. So we also know that the displacement, okay, the displacement in the y direction is, it's going down in a downwards direction. So we know the displacement is going to be negative 828 meters, because remember it's in the downwards direction. We're displacing motion. We can find out how long it takes for it to actually get down there, and that one's actually quite easy. Alright, let's have a look. So if we know, let's work it out. If we know that the displacement, and let me go down a little bit here. No, let's stay here. Let's stay in this part. Okay. We know that the displacement in the y direction is given by ut, or uyt, plus half of a in the y direction, t squared. Okay, and that one, so we have uy being 0 times t, which is going to be 0. And here we're already going to put minus, because remember we're accelerating in the downward direction, minus half of 9.8, it's going to be 4.9 multiplied by t squared. Okay, so and our displacement is negative 828 meters. So this will be 0. So in order to get, I'm just going to skip the maths because you should be able to rearrange that really quickly. So t is just going to be square root of 828 negative, sorry, negative, let me get that in red so you can see it, negative 828 divided by negative 4.9. If we just plug it into our trusty calculator, it's going to be square root of negative 828 divided by negative 4.9. So it should be around about 12, so time, let's put it in purple, should be around about 12 point, no, get rid of that. So it actually ends up being rounded very, very close. It's 12.999, so we'll round that to 13 seconds. Beautiful. So now we have time. So we know how long it takes for it to actually get down to the bottom in the y direction, but we know that that's also the same amount of time that it actually gets to this point. So the time is constant. Time stays constant in this motion, because remember, time doesn't have a direction. It will stay constant in both the y and the x direction. Very good. So now we should be able to find now the actual, let's find the distance. Let's find the distance it actually takes to go over there. Now, a little bit of intuition will give you that, and I can already tell you that in the x direction, so in the horizontal direction, time acceleration, there will be no acceleration in the x direction. The velocity will stay constant given that air resistance is negligible. The velocity will stay constant in the x direction. So knowing that, if we know that our initial, okay, I'm going to take that down here, knowing that if our initial velocity, actually let's do it in orange, our initial velocity in the x direction, okay, is 58.2 meters per second, which is actually the same as the final velocity, because remember, velocity equals constant. It's the same as the final velocity in the x direction. We can just simply work out that the velocity in the x direction is the displacement in the x direction divided by time. And in order to actually get our displacement in the x direction is just our velocity in the x direction multiplied by time, which is 58.2 meters per second multiplied by 13 seconds, and that should give us 756.55 meters. Okay, so beautiful. So we've answered both questions. We've answered them really quite well. We've answered how long it takes for it to actually get to the end of the motion and how far it is actually kicked in that direction. Now there's one more type of question that I might actually ask now, but I'll answer it in a different video because it gets a little bit, the maths gets a little bit more complex. We're going to have to use a little bit of trigonometry. Can we figure out then how fast the ball is going by the time it hits the ground? So what is its velocity? So we'll try to find out its actual magnitude, the actual velocity, and its position. So then you'll need to find out its angle at which it actually hits the ground. Now we can actually find that out, but I'll answer that in a different video. So I hope that was helpful, and I hope you should be able to get to the point where you should be able to find out the time given the initial velocity at the top of that sort of half an elliptical motion, and you should be able to find the displacement. So I hope that was helpful.